Recording.
Okay. I am ready. I just need to share my screen. Yep, I have the ability
I made you
to.
co-host. Oh, Damon, I'll make you co-host as well.
Can everybody see my screen?
Yeah.
Yep.
Hi. Okay. Well, welcome. This is about causality. My name is Scott Mueller. I think many of you know my son, Ken Mueller. And I'm right now a grad student at UCLA for computer science. So my main research area, what I'm really passionate and excited about, is causality or causal inference. And we're going to discuss what that is, causes and effects, and how that applies to computer science and in particular machine learning and artificial intelligence. So I'm going to have what I hope is a discussion here. So I want this to be interactive. If any of you have any questions, please announce them. I don't know if, I think everybody is unmuted here, but please speak up, raise your hand. I hope I notice the raised hands or type in the chat, because otherwise, if it's just me talking the whole time, this has been a video and you can watch it online. But I think I can provide more value here if it's interactive. So I'll be talking about causes and effects, which is basically what causality is all about. There's effects of causes and causes of effects, which is a fun distinction. We'll talk about determinism versus probabilistic nature of things. We'll talk about probabilities. I don't know how familiar all of you are with these, but we'll go over some of the basics and experimentation, how that applies to scientific discovery and how it applies to understanding the true nature of things. We'll talk about counterfactuals, which is a really exciting area of causality that is not able to be touched on in traditional statistics, especially not machine learning. And we hope to change that. It's starting to. So ultimately, we will conclude with how all of this applies to artificial intelligence. Let's begin. Are all familiar with this diagram? Or can anybody say what this is about? Why do we have a circle around an X and an arrow pointing to a circle around a Y? Or any guesses?
It's one circle pointing to another. I wonder. Right.
I know Claire knows. So I'll just answer this for you, but Charlie wrote, I bet it's a linked list. No, not a linked list, but that is, there are similar diagrams for lists. I can't see all the, there's a bunch of chats pushing other higher. So if somebody answers something and I don't notice it, I apologize. You'll be one of the first to answer it and it went up above everybody. But I see Neil says X causes Y, and that's basically it. So we want to understand causes, and actually so we draw a causal diagram, which is what we have here. X causes Y. And that's not just for us to be able to visually see what's going on. It also plays a significant role in being able to calculate the probabilities and the various estimates and values that the quantities that we want to determine in various scenarios, which I think is really interesting about causality. So we have X causes Y here. What are X, Y? What's an example? What might X and what might Y be? Any guesses or stabs at this? Feel free to just yell it out. Oh, go ahead.
Crime ratings.
Sorry, say that again.
Video games and crime ratings.
Oh, so which one's X and which one's Y?
From the popular opinion that from people who think that they cause that video games cause violence and higher crime rates, then it would be X would be video games, Y would be higher crime rates.
That's right. That's a great one. Could it be the other way around? Higher crime rates is X?
Well, I mean, like if a lot of robberies, you have more money to spend on video games, but
Right. Or maybe it's part of the culture. And so people just have this fascination with crime because they see it. And there are a lot of criminal type video games, right? Could be. But the more natural assumption would be that video games might cause crime. So does anybody know the answer to that? Is that true? I know the answer to that. I know I've seen that question posed, but there are probably many other factors involved if there is an influence at all. There is an influence. It's not a complete 100%. If you play video games, that doesn't guarantee you, even if video games does in fact have an effect on your willingness or desire to do crime, it's certainly not going to be a 100% deal where it absolutely causes you to. So this is, at the very least, if this was a causal diagram where X was playing video games and Y was committing crime, this wouldn't be a complete diagram, because in that case, then we might say that you play a video game and it is absolute certainty that you will commit a crime. Here are some other examples. I see a bunch of other chat messages here. X equals ice cream sales, Y equals diabetes. Okay, that's an interesting one. Does ice cream sales cause diabetes? Indirectly, maybe. And so we might want to put in a few nodes in between X and Y. So here we have medicine and cured. X would be medicine, Y would be cured. You have some disease, you consume some medicine, and either swallowing some pills or drinking some liquid, and then hopefully you're cured. If you study, you should ace the test. If you flip a light switch, the lights should turn on. Hopefully flipping the light switch causes the lights to turn on, right? So then the question is Y perfectly predictable? What about the last one? So we know that medicine doesn't always cure you. Unfortunately, if you go through chemotherapy, that doesn't mean that you're going to be cured of cancer every time. If you study for a test, you still might not ace that test. Some of you might have experienced that already. Hopefully not too many. Probably all of you. If you flip a light switch, though, would that make Y perfectly predictable? Well, not really, right? So light switches fail, right? Sometimes I'm sure some of you at some point in your lives have pressed the button to turn on the light or flipped it upwards and the light didn't go on. And that's frustrating. You want that light on, maybe. Well, why wouldn't that light have turned on? That seems like a perfectly natural causal scenario that should happen. The house will explode. Eric wrote that. Any other reasons why the light might not turn on? Well, we'll revisit this actually, because I think that's a fun toy example. But maybe we just need to add nodes. So as an example, study and acing the test. We all know that sometimes you study and you still don't ace that test. But then this is not a complete causal diagram. X doesn't cause Y 100% of the time. So there's something else going on. Why might we study and still not pass the test, still not ace the test? Anybody, has that ever happened to anybody and you've thought, wait a second, what's going on? Because you were in a bad mood? Yep. You slept in, okay, you had a robbery. All right. Or maybe this is not an interesting subject And so you study a lot, but it was just so boring and so not interesting that even though you read that material, you understood it, you don't remember it. It just went right out of your memory because you didn't correlate that with anything else you're interested in your mind, or have that encoding, yeah, you're sleepy. You just had a momentary lapse in judgment on the exam, even though you knew the material. So we need to add some more nodes here. Here's a Z node. Y is acing the exam. X is studying. Well, there's something else contributing to acing the exam as well. And we can think of this as sleeping in or engaging material, how much you enjoyed that material. So we might need to add 100 nodes. And we can add them in different ways. So Z not only might influence Y, acing the exam, but Z might have influenced X as well. So let's go back to the studying and acing the exam. What might Z be that affects your ability to ace the exam, but also have an arrow going into X? Your time studying. All right, I like that. Right? That makes sense. Your time studying will affect your studying, but that might just be X, right? You study for the exam is the amount of time you study for the exam. Let's see, playing outdoor games. So if you play outdoor games, that could affect your time studying, but would playing outdoor games affect your ability to do well in the exam? I don't know. Your instructor. That's a good one. Will your instructor affect the amount of time you spend studying? How effective is your studying? Okay, well, definitely effectiveness in studying will affect Y, but will effectiveness in studying affect the time you spend studying? Is your phone nearby? Interest. I think Annabelle has it best. Interest. If you're not interested in the material, then you're probably not going to do well on the exam for a variety of reasons. You just don't think deeply about this because you don't enjoy it. So even if you know the material, maybe applying that in interesting ways and creative ways, your mind just doesn't quite go there. But if you're not interested in it, you're probably not going to study it that well either. And even if you spend 8 hours studying it, maybe 4 of those hours were actually studying it. 4 of those were getting distracted because it was just so uninteresting. Okay, so we know the basics now of these causal diagrams. Is anybody here familiar with DAGs? Or does anybody know what the acronym DAG stands for, DAG?
Diacylglycerol.
In the
Directed acyclic
context,
graph.
yeah, directed acyclic graph, right. So causal diagrams are always DAGs, directed acyclic graphs. And what that means is they're directed, so they have arrows, but they're also acyclic. You cannot have a situation where Z causes X, X causes Y, and Y causes Z. Now that's something that causal scientists put into place, that, hey, we can't do our amazing formulas if there are cycles in the graph. But actually, it doesn't make sense to have cycles in these graphs. Why not? Why can't we have Z causing X? So Z is interest, X is studying. Circular reasoning. Well, you can have circular reasoning. I mean, maybe it's not productive. Cause and effect. Yeah, I mean, that's kind of the core of it. You can think of it as, if something causes something else, it needs to happen before it, right? In time. And so if Z causes X, Z has to have happened before X. We're going to take away the time travel possibilities and other phenomenon that we don't know really exists. But Z causes X, so Z happens before X. X causes Y, so X must happen before Y. Well, then Y can't cause Z because Y has to come after Z, the transitive property of time. All right, so I'm going to go to the next slide. This is, we're going to go in a bit more depth. By the way, Claire, how much time do I have? Maybe I need to go a little faster. Anybody know how much time I have?
Oh, sorry. Yeah, you have time. You have until 6:30, I believe. That's
Okay.
when Damon starts. Yeah.
Okay, so I mentioned some things here that are considered toy examples. Flipping a light switch and the light turning on. That's not something scientists. Well, if you're the manufacturer of a light switch and a light bulb and houses, you care about that, and you might even do experiments and that kind of thing. But generally, it's not something scientists occupy a tremendous amount of time with. But medicine cured, if it was chemotherapy and radiation therapy and other medicines to cure, that's something that's very serious. So you often see in the literature on causality these two extremes. Some really simple toy example. I'm writing a paper right now on a coin toss game, which has all these fascinating implications. But these are toy examples. But then you have these serious scenarios. But the toy examples allow us to conceptualize the math involved to apply them to much more interesting, serious, consequential, impactful examples. So determinism. Anybody know who this is?
Darwin?
Well,
Not Darwin.
Oh,
Descartes?
oops,
No.
Descartes. Wait, no.
Spinoza. Kai, very good. Right. He's a very famous philosopher, and he's a Jewish Dutch philosopher, and he had a problem. So he was expelled and shunned by Jewish society when he was just 23 years old. He goes down in history, and if any of you study philosophy or other subjects that he was involved in, you'll read about him quite a bit. So he's very influential. Why was he shunned by Jewish society? That's really a shame. And the reason is because he said that causal knowledge. So right away, but this happened a long time ago. Causality's been around a long time, but it's only recently that we've made some really interesting progress in causality. I'm very, very fortunate to have the opportunity to work with Judea Pearl at UCLA, and he's been extraordinarily influential in causality over the last, I don't even know, 20, 30, 40 years. First inventing Bayesian networks, and now coming up with so much of the math behind causality and counterfactual reasoning. But he thought about it quite a bit back then, Spinoza, and he said that if we have complete causal knowledge, we know everything, all the causes. We know the complete causal diagram. We're going to go over Bayesian networks? No, not at all here. That's just something that my professor worked on quite a bit earlier on in his career. But you can look that up. They're still very, very useful. That was the transition from him into causality. But here it's pretty interesting. When I'm sure a lot of you have thought about it, when you want to find out something, well, you've got to know the causes, and then you can make those predictions. But if you really knew everything down to the atom, down to the subatomic particles, there's nothing you can't know, or at least that's what Spinoza. Sounds like Devs, right? Alex, yeah. So Devs is a great TV show. I enjoyed it. It was only one season, but it was pretty fun. Anyway, so imagine we have all the nodes in those causal diagrams I showed before. Imagine we have that for a person, and we have every node for every atom, for every subatomic particle, for how those are spinning, how those are interacting in their brains and the neurons, and we understood it all. Then we can encapsulate all their characteristics and desires Every atom is accounted for. And then ultimately, below Laplace's demon, Ryan. It's very good. I'm gonna that comes at the end of this slide, right? So everything could be determined, and that includes, well, you take chemotherapy. Are you going to be cured from your cancer, or maybe you need radiation therapy? Maybe maybe you wouldn't have been cured from chemotherapy, but you would from radiation therapy. Well, that's very, very important information for yourself. I mean, one decision which is very difficult to determine. I don't know the specifics medically when you should take radiation therapy or chemotherapy, or when it's a difficult decision. But I know sometimes there are difficult decisions you have to make where one could be the wrong decision could end up with you dying, and the right decision, you could have survived. So those are some pretty important things you wished you could know. But you could even know what your next thought would be, and what your next thought will be 100 years from now if you were to live that long, if you have everything, all the causal codes. But of course, we can't know everything, or and even if today we have such incredible sophisticated machinery to know much more than today, there are actually some limits in physics on what we can know. The Heisenberg's uncertainty principle, right? So we can't measure, or the more we measure the momentum of a particle, the less we can know the position of that particle. I know there's a bunch of uncertainty principles of that nature. So at the end here, I have Laplace's demon. This quote was by Pierre Simon or Simon. I don't know how to pronounce the names, but Laplace. And I think he wrote some really interesting stuff on this. So if any of you are curious and enjoy this kind of philosophy, this is fun. I'll just skip this in the interest of time. Probability. This is something I hope all of you will learn and really enjoy, because as I'll mention, we live in a probabilistic world in multiple ways, and understanding probability, I think, is so valuable and important in many things you'll do in life. So here's a quote. This quote is by Jonathan Winters. Nothing is impossible. Some things are just less likely than others. But actually, some things are impossible. And so we say when something is impossible, that it has probability 0. Who can tell me what the range of probabilities are? How we measure probability? What is the numerical? 0 to 1. That's right. If something is a probability of 1, that's the same thing as 100%. We're all familiar with something being 100% probable. That means it's with complete certainty. But if something's probability is 0.5, 1/2, that means that it could happen 50-50. So we can say that a probability, we can define it as the likelihood that events will occur, or that a particular event will occur. And we can quantify it with the number of desire. Sometimes you can quantify it like this. Sometimes we don't have these discrete outcomes that we can measure it in this way, but often we can. We say we take the number of desired outcomes and we divide it by the number of total outcomes. And I'll just give some quick examples here for those unfamiliar. If you're rolling a dice, I read, but I'm still a little uncomfortable with it, that die is no longer refers to a single dice, or it's one of a pair of dice. You actually say dice for even just one of them. So I'll state that here as such. So if we roll a dice for a 5, that's just one of them. What is the probability? Anybody want to say that or type that? 0.2, close. Rounded, that's correct, John. Yeah, 1/6. So one desired outcome over 6 total outcomes equals 1/6, or 0.16 with a bar over it. The bar didn't quite make it over here. I think Google Docs doesn't render that character so well. But John had that right if you round that to the nearest tenth of a decimal point. Rolling 2 dice for a 5. Anybody know that? So you just have to count the number, what are the number of total outcomes? 36 is the number of total outcomes, that's correct. But not 1 over 36, because how many desired outcomes are there? Remember, there are 2 dice. So there's 2 ways to, there are 2 dice to be able to add up to a 5. So let's see, Tomas, if I pronounce that right, hopefully. Tomas said 4 out of 36, which is 1 out of 9, because for the 2 dice, it can be a 1 on the first dice and 4 on the second, 2 and 3, 3 and 2, and 4 and 1, and there are 36. We can see here order matters. You can also calculate this in a different way where order doesn't matter. Hopefully some of you will learn those kinds of combinatorics. And that is 0.1 with a bar over it. Rolling 2 dice for a 7 or 11. Who knows what casino game this is for? Yes, Ryan. This is involved in the casino game Craps, which if you read one of Judea Pearl's books, he has some interesting probabilities on that. But any book on probability, not any, but a large number of books on probabilities have some casino games in there because they're kind of fun to estimate how much money you win. 8 desired outcomes for here. We can have 1, 6, 2, 5, 3, 4, all these. And of course, there are 36 again still. So now it's 0.2 with the bar over to 2 nights probability. So probabilities are really important. And well, who can tell me why probabilities are important for life? It's how I learned Python. Probabilities are how you learn Python. Many things in life can be measured with probability. True. Well, one reason is even if you do believe that indeterminism, as Laplace and Spinoza did, and many other people did, and many people today do, we don't have all that information. So in order to estimate outcomes, which is pretty important if you want to make good decisions in life, you've got to use probabilities. How often do you make decisions? Or decisions that matter to you, that you make the right decision? Pretty often. And sometimes those decisions can literally be life-threatening or life-saving. So probabilities are very important. And I encourage you all to have a lot of fun learning them. I certainly enjoy them. And then, of course, for those of you familiar with quantum mechanics, everything turns out to be probabilistic. I found that pretty interesting when I first learned that a long time ago. First learned about quantum mechanics. We think. So it turns out that it looks like Spinoza and Laplace were wrong in multiple ways. Not only wrong in the sense of the Heisenberg uncertainty principle that we can never measure everything. Even if we're as advanced as a civilization can ever be, there are fundamental limits to that. But even then, it turns out that everything it looks like. I'm not an expert in this area, but from what I hear, everything turns out to be probabilistic fundamentally. You get down small enough. So we live in a probabilistic world. Everything, and so ultimately, probability is about expressing our beliefs and uncertainty about the world. That quote is from Causal Inference and Statistics, a primer, a book I highly recommend everyone purchase, read, study, and really grasp. This is one of the books that is written by Judea Pearl. It is amazing. It is a small book. I think I don't know, 127 pages or so, roughly, and I think not too difficult. This is a book that I taught with some of you here have taken my class, and we went through the book front to end. And I think everybody in that class was between 12 and 14 years old. So it's certainly a readable book. Probabilities overcome our limitations of our knowledge. Time is 6:05. I think we're good. This is what I was discussing before, that we think that we can know everything if we just have that causal model, a complete causal model, but we can never get that complete causal model. There will always be limitations of our knowledge, and probably not to the degree where we need to know exactly every position and spin and velocity and momentum of each subatomic particle, but there are much more basic limitations of our knowledge of a situation. And so we have to use probabilistic ideas for understanding and solving those kinds of problems. By the way, like, I'm talking a lot, and I do want this to be interactive, and I think it's more valuable to you if you ask me questions along the way. Feel free to interrupt me or raise your hand. Hopefully nobody's raised their hand and I didn't notice it. If you do hand and I don't see it, just shout out. So like I said, underlying everything, probabilities at the quantum level. This is the world we live in. This is our universe. This may be just the nature of reality. Right. We can never add enough nodes to, even if we do have that complete causal knowledge, even if we overcome Heisenberg's uncertainty principle. So now leading into science, much of science is discovering two things. Who can tell me what those two things are? When we think of science, either chemistry, physics, biology, what are we trying to learn? What are we trying to understand? Or evidence, good. Math, right? Phenomena, right? Well, so evidence and phenomena, we see some phenomena, right? We see the stars moving around us at night, going from one end of the sky to the other. And so we want to understand what when we see that. We see the sun rising and then falling, rising in the morning and falling at night. Where do we want to go with that? What is science trying to do with that information, that phenomena, explanation, right? We're trying to get the effects of causes or the causes of the effects. We see the effect of the sun rising and falling. We want to know what's causing that. Are we at the center of the universe and everything is spinning around us, including the sun? Or is there another explanation? And so that's where science tries to understand, given all the evidence, what's happening. So we'll start with effects of causes. And here's an example. We have a cause, which is what in this example? The cause here is taking medicine, right? We want to know what's the effect of that. Will we be cured? Or will there be some other effect, commonly known as side effects? Maybe we are cured, but we also have really, really bad headaches or other issues. And maybe what we're being cured of is not that bad. It's not cancer, but it's, achy joints. But the headaches are so bad, we don't want that. So that's the effects of a cause here. Medicine, probability of acing a test from studying. So this is something we discussed in the very beginning. The cause here is anybody? Studying, right, Alex? And the effect is acing the test. So if we try to understand the probability of it, we can come up with a probability, right? We can look at the history of all the times we've studied a certain amount, and we can see what the results were, a percentage on our test, or if or some threshold level that we say, oh, okay, above 98, we aced it. So did we ace it or not? We tabulate all those results, and we can get the proportion of times that we aced the test after having studied for 8 hours. So we can calculate that, but it won't be very accurate. It won't be very helpful necessarily in predicting how we'll do on the next test. And that's because we need to get some more information. And so one of the pieces of information, maybe if we're looking at as a whole, at a population, maybe the population of a particular class, we want to know what's the probability that this all these students will do well from studying 8 hours on this exam. Well, we might want to segment that. I want to say, well, okay, now let's only look at the people that have 175 IQ, and maybe there's only one person, and so we say, okay, for that person, we have to only look at their test results. We can't pool together everybody else's test results. So here I said we're going to come back to this toy example, probability of light turning on from flipping a switch. How can we find out the probability of that? Any thoughts on that? Feel free to shout out your ideas. Flick it many times, right? We could do that. Of course, you know, if we just go up and down, up and down, up and down with the light switch, it might work perfectly well now, but we know that each day is different. So maybe we've got every day until it breaks. Probability of its components failing, Alex, very good. So the probability of a defective bulb is 0.01, 1%. 1% of the time, let's say, every time you turn it on, because we know you turn on that particular light once a day, and we know that on each day there's 1% chance that the light has burnt out or went bad for some reason. So that can inform us quite a bit what the probability is of the light turning on from flipping the switch. That's the only thing that really we need to be informed of. Is there any other reason why? Is there any other probability that we need to include in our calculation?
Maybe the power goes out or the wires break.
Yes, wires break, right? So the power could go out. Maybe we don't know that because
Power going out is a non-zero probability these days.
That's yeah, absolutely. Most things are non-zero probabilities. They might just be very close to zero, but probability of power going out, if you live in Texas or some areas nowadays or lately, you might be kind of high. But I didn't see probability of EMP. Maybe the light bulb doesn't work, so the switch itself won't. Right. So the light bulb doesn't work. Yeah, we can say that's a defective bulb, or the light switch broke. Right. Now the probability of a defective switch might be much smaller than the defective bulb. So the effect of that switch, or the role it plays in determining the probability of light turning on, is much smaller than the bulb. The bulb is probably the number one reason, not living in Texas nowadays, it's probably the number one reason why the lights wouldn't turn on. So you know, you put all these probabilities together into a particular equation that we're not going to go over right now, then you can figure out probability of light turning on from flipping the switch. That's the effects of causes. But then we can go the other way. We can see the effect, the consequence of the phenomena, and we can go backwards and try to understand the causes. And that's sometimes a very interesting question. And here we can think about the light switch example again. We see the light, and we see the light on, what's the probability that the reason it's on is because somebody flipped the switch up? Any thoughts on that? I'm in Florida. There's a significant probably of a storm blowing down power lines.
Well, it's probably like 1 minus the probability of having a defective switch.
Okay, so you can have a defective switch that operates the other way. It's not that you turn it on and the light doesn't come on, but the switch it just turns on the light and you don't even want it to. The powers, the switch is in the down position, right? So that's one reason, one cause for seeing the light. There could be others as well. I can't find my brain. Vishrut says the wires aren't connected right. Yeah, something happened with the wires. There was a cross wire, some mouse in the wall chewed on the wire and connected the wire that goes to the light bulb to a different switch that happens to be on. There are other reasons that may have a very, very low probability. But that's what we try to do sometimes. And the probability of having a flipped switch when we see the light on is very high. It's not 1 or 100%, because there could be other reasons, but it's high. This is a more interesting question maybe for those of you who are into astronomy. When we see that a star's light dims as we're pointing our telescopes to it, what is the probability that that was due to a planet passing by it? And that's one way, I think the main way that we understand how other solar systems work far away. Okay, experimentation. Oh, 6:17 already. I gotta go a little faster. Slide away on slide 7. Okay, so we as humans, we do this instinctively. We try to infer causes when we see some phenomena, right? But how can we be sure? How do we even start to imagine what causes might have been at play to when do we start? When do we start thinking about these things? Does anybody know? Researchers have actually experimented. I taught another class on decision making, and we read the book Thinking Fast and Slow. Some of you here took my class on that, and and that book mentioned when we start thinking about causes, when we start understanding it and what we do, how do we do it at such a young age? Anybody know the age? Apparently less than 1 sometimes, even as infants, what we do, even when we're playing with blocks. So we refer to it, this happens all throughout our life, but we start very young. Playful manipulation. We manipulate the scene, the scenario, what's in front of us, and we try to understand what's going on. We pull a block out at the bottom and all the blocks fall. We realize, oh, that's a cause of blocks falling. Also see Damien says between the ages of 4 and 6 for most people. Yeah, okay. And so what is this? Children first learn cause and effect at 8 months of age, right? Very good, Kai. I'm gonna click on that after this. Okay, so playful manipulation is essentially experimentation, but maybe not so rigorously as we learn in advanced college classes or sometimes in high school. But we can basically come with hypotheses and we test them. We think that something fun is going to happen when we put this block, and we imagine that blocks are going to fall a certain way, and maybe we realize, oh no, it's a different way. And so we do this in a much more sophisticated way as we get older and as we get sophisticated academically, and we want to know if a medicine works. We have reason to believe that it might work. Some kind of evidence that tells us we should try this. And so we try it. Does anybody know the main way that we test medicine? The gold standard, as it's known.
Trials?
What's that?
Clinical trials, I believe.
Yes, clinical trials. And within those clinical trials, we have randomized controlled experiments or randomized controlled trials. And then here, it's very important that it is, in fact, randomized perfectly. We need to separate people into control and treatment groups and give the treatment group the medicine and make sure the control group does not take the medicine. Even if we don't give it to them, they don't, maybe we're testing the effects of Tylenol. And we, and you know, you don't need us to give you Tylenol, you can go buy it, or maybe you have some in your purse or on yourself and you have a headache. But in for this trial, we've got to make sure that everything is perfectly controlled for. And so it may, I'm giving a hypothetical trial of Tylenol takers and non-takers. So we then look at the difference in outcomes, right? If you were forced to take some medicine and not allowed to take some medicine, well, then we should be able to get a pretty good idea of if the medicine was effective, assuming that it was perfectly randomized, which means the distribution of people, the demographics, right? Double blind, making sure the experimental procedure is good is very important. Double blind is a way to do that, where you as the participant in the study, you don't know whether you're in the control or treatment group. And there are a variety of ways to do that. You can, if it's a pill, you can give them a sugar pill or the real pill, have them look exactly the same. Double blind means that not only do you as a participant not know whether you're in the control treatment group, but the administrators don't know either, because sometimes that can be that can influence the results. You have to be very careful. But let's assume that the experiment is conducted perfectly well. Then we should be able to get causal knowledge, right? We should know how this medicine causes your outcome, or the probability that it cures you, if you separate people into treatment groups and control groups. And in clinical trials, this is the gold standard. So, you know, sometimes you can't do this. There are a variety of reasons you can't do this. There are ethical reasons. Sometimes it's not feasible, but typically this is how you do it. So, but there are fundamental mathematical limitations to the information you can get from randomized controlled trials, and sometimes those can have really important consequences. And most people don't know this. And so here's an area where causality plays an interesting role. And here is an example. So proportion cured and given the medicine. So you can imagine you give the treatment group medicine and a certain proportion of them are cured of whatever ailment or illness or disease they have. Maybe to take it to an extreme, they have a life-threatening disease and they survive. So let's say that 75% of people are cured when you give them the medicine. Well, that's good for those 75% of people, and not good for the 25% of people who didn't survive. But that doesn't tell you if the medicine is effective. Why not? Chocolate-covered pills. You guys are pretty funny in your chat comments. But can anybody see what's wrong with? Is 75, if the proportion cured when given the medicine is 75% or 0.75, is that a good thing or a bad thing?
It just means you don't understand like the attributes between the people cured and the people not cured.
True. But the important thing here is, at least it would be, we don't know if 7% of people is good or bad until we know, well, what happens for the people that didn't take the medicine? If the people that didn't take the medicine, 100% of them are cured, which means this disease was actually not life-threatening at all, then what would you say about the medicine? 75% are cured when they take the medicine. 100% are cured when they don't take the medicine. If you're faced with this disease and given this medicine, are you going to eat it or swallow the pill? It is an anti-medicine. Yes, Montaser. I don't know if I pronounced your name right, probably. Right, it sounds like bad medicine, right? It sounds like it has a 25% chance of killing you. That's not good. But if this medicine, the proportion of cured when taking it is 75%, same for 75%, but the proportion cured without the medicine is 0. It is not only life-threatening, it is a killer. You are going to die if you have this disease. But when you take the medicine, 75% of the time you survive. Wow, this is a miracle drug. This is incredible. This is a Nobel Prize winning medicine. So this difference is very important. And that's what clinical trials are all about. So if what does it mean if the proportion cured when given the medicine is 100%, and when you don't take medicine, it is 0%? We kind of went over that. That means this medicine is a complete cure, and it is pretty amazing. And in fact, this medicine, not only is it amazing, but the probability of it curing you is, if you take it, is certainty, and you dying without taking it is also certainty, which is pretty extreme, as extreme as you can get. Here's an interesting question, and here's where RCTs fall or falter or have some. It's clear there are some limitations. If it is 6:27, so I've got to go fast, but if it's so if this difference is positive, that means the proportion cured when given the medicine is bigger than the proportion cured without taking the medicine. That's good. That means the medicine was, if you're faced with this disease, you'll probably want to take the medicine. And if this difference is negative and you're faced with this disease, you should probably stay away from the medicine. What I just said is not necessarily true, because you may have some genetic marker, or maybe this medicine works much better on females versus male, and so it depends on your gender, and knowing your gender and knowing how it affects different genders, that may change your desire to take it or not. But in general, if you don't know any other information, then it's harmful if this is negative. And so the question is, what if this difference is 0? If it's a 75% chance that you are cured when you take the medicine, but it is also a 75% chance that you're cured when you don't take the medicine, what does that say about medicine? It does nothing. Human number one says. Tomas also says it doesn't do anything. Well, how do you know that? Actually, this is one of the limitations of randomized controlled trials. You actually don't know that. Medicine still could be an amazing medicine. But so you think, well, how can it be amazing if the proportion cured when given the medicine is the same proportion cured without the medicine? So it doesn't matter whether you take the medicine or not. Well, it might matter very much, because 25% of the time, the medicine might have absolutely cured the person, whereas if they not taken the medicine, they would have died. And then you say, well, that should be over here too. Then we should have seen that in the proportion cured. It should be 25% less, but it might have actually hurt or killed 25% of the people. That's why you don't see it here. I've got to move kind of fast now. Sorry, are the limitations to what experiments can tell us? And yes, that's one of the limitations. So we're going to talk about counterfactuals now. Interested in code, using code in math and science. Oh, so here. So counterfactuals. This is really a fascinating area that causality is tremendously helpful in understanding. Here's a quote from the book that I mentioned before, Causal Inference and Statistics, a primer. If I had taken the freeway, I would have gotten home earlier. In the book, in the beginning of chapter 4, Judea says, he took the freeway and he noticed a lot of traffic. So he took side streets and he said, oh no, it turns out side streets it took me an extra hour to get to where I was going. But so then wait for a little bit, however, for those hoping to attend the end of this discussion. Okay, yeah, so if you want to stay on a little longer, so the question is, had he taken the freeway, would he have gotten home earlier? And there's a big problem with that question or that statement. We don't know. It's you can't know. If you had not taken the freeway or that decision has not yet been made, this is a counterfactual statement. And counterfactual statements are counter to the facts. You did something, now you want to know what would have happened had you not done that thing. Well, that's not what happened. So how can you even ask that? You can't go back in time. But we can actually answer that. We can get probabilities around that. And sometimes we can get very specific probabilities, and sometimes we can only get bounds on those probabilities. We can say the probability that you would have gotten home faster had you taken the freeway is between 0.1 and 0.15. And those bounds can be very informative into your decision making. So these are, I'll just skip ahead. These are both counterfactual statements. I'll get home less than an hour. I'll get home earlier than not. Well, you don't. These are comparing two different outcomes. So one of them might be true, but the other one then wouldn't be true. Notation. We use variables like in math or programming, x, y. X takes on the value instead of 0 and 1. Often we say x or x prime. And y, instead of 0 or 1, we say y is equal to you got home earlier, y prime means you got home later. So we can say the probability of y dx is probability of that you would have gotten home earlier had the freeway been taken. And this may be true. You may actually take the freeway and then you would know whether you get home earlier. You wouldn't know the probability necessarily because maybe the probability is very, very low, but you got lucky. And so it turns out, yes, you get home earlier. But if it's a comparison, then it's a counterfactual. And so here's a counterfactual statement. Here it's saying, I don't know how many of you know this this probability notation, but x prime, when it's after this vertical bar, that means given x prime. So we want to know the probability of something given that in here we took the side roads. We took the side roads. Now, what's the probability that y based x, which is that we would have gotten home earlier had we taken the freeway? So that, the type of question that you'd normally think, well, we can't ever know that, we can't go back in time, but we can. So, but we know we can make some assumptions. We can do a lot of things. Sorry about that. My wife is having trouble, but I think she's fine. So necessity and sufficiency. This is a very interesting probability. We say probability of necessity and sufficiency, meaning in the context of the drug example, or the drug or the medicine curing your disease, we say, what is the probability that this medicine was not only necessary to cure your disease, but it was also sufficient to cure your disease? Which means that had you taken the drug, you would have been cured from the disease, but had you not taken the drug, you would have not been cured from the disease. And that's often the core question we really want to get to in life, in science, and that's called the probability of necessity and sufficiency. You can also think of it as the probability of benefiting. How much did this medicine really benefit you? Meaning you might have taken it and you got better, but you would have gotten better anyway. So it didn't actually benefit you, even though you took the medicine and you got better, which is which is a very, very important distinction, and something that many people get wrong when they think about probabilities and when they think about causality, and they look at tests and tests in the sense of clinical tests and experimental tests. So I think one interesting aspect of this is that this was a Twitter conversation that Judea pointed out at some point in the last month or so, 2 months ago. I thought was fun. When you say thank you, that is, I ask you, it's a counterfactual statement, but we're over our time, so I'll just tell you, yes, the counterfactual statement, which is odd, right? When somebody does something for you, or you think, why do you say thank you to somebody? Can anybody tell me why you would say thank you to somebody? And let's remove the times that you say thank you to somebody just because it's just something to do. Why do you say thank you to somebody and you really mean it? They did a service to you at their detriment. Okay, well, let's take away the to show appreciation. But why do you thank somebody? Even if you don't verbally thank them, why do you thank them? Maybe you do it even in mind. Rules that exist in society, Tomas says. But I like they did a service for you at their detriment. It doesn't have to be at their detriment, right? I mean, you could still be very thankful to somebody because they did something, even though it wasn't at their detriment. It didn't really even cost them anything, but it still did something for you, right? It was a benefit to you. You appreciate what they did. And why would that be counterfactual? The reason is because the person did or said something and you had a good outcome, right? They helped you with something. They cleaned your room. Now you didn't have to clean your room, right? They cleaned your room and it got clean. It's a great outcome. You needed it clean. You were going to get in trouble otherwise. But had they not cleaned your room, you would have had to, or it would have remained dirty and you would have gotten in trouble. So however, what about the situation here? Oh. So if the probability is high enough, you say thank you. Otherwise, you can still say thank you, but you don't really mean it. And here's an example of something that someone does, which you're not really thankful for, but they did something for you, and it was correct, and you had a good outcome. So you're working on homework for a causality class or math class, and you know the answer to question number 1. It's an easy one. Everybody knows it. And your friend tells you before you even write it down. Your friend says the answer is 5. Well, you knew the answer. So you might say thank you. Okay, yeah, thank you, but you weren't really thankful. The next workshop needs to start. Okay. Oh, I thought actually the next workshop already started, and I'm just here for people who want to stay on. Okay. So let me just data from causal graphs, artificial intelligence. Today's machine learning algorithms, they are really, really impressive, but they are only correlations in the data. They're only looking for patterns in the data, and machine learning does not understand causality yet. We are starting to. There are a lot of interesting new research in this area, but I very much believe that this is the future of AI and machine learning. This is what's going to get us to human level AI. Thank you.
Thank you so much.
You're welcome.
Thank
Bye,
you.
everybody. Hope you enjoyed.
Thank you. Yeah, I really
Thank you
enjoyed
so
it.
much.
You're welcome.
Yeah,
Even though
thank you.
I came